Last week in lab, you guys submitted your first milliliter of distillate collected in an autosampler vial. What we did after lab was run your samples on what's called a gas chromatograph. And we're going to have you guys analyze the data that it produced to determine how much cyclohexane versus toluene came through in your distillation. So this video is really not going to be about this week's lab, which is thin layer chromatography, but it's really going to be introducing gas chromatography to you. Now, in order to understand what gas chromatography is, the first thing that you have to understand is what chromatography is in general. It doesn't matter what chromatographic technique in particular you're using. All we mean by chromatography is we're going to separate a mixture of components by passing that mixture through some kind of medium in which each of the components flows through that medium. It moves through it at a different rate. And so if you have a mixture of two things like you did with the cyclohexane toluene, one of them is going to move faster through that medium, and so it will come off first, leaving the second one to come off second, and thus you've separated them. So just for a graphical illustration, let's look at, and I'm very sorry if you are colorblind, I didn't even consider this when I did this, but let's imagine that you have two components that are each denoted here by red dots and green dots, and these are in a mixture and you need to separate them. What you can do is pass them through this material. And let's say when you put them on, it turns out that the red material can flow faster through that medium than the green material. So at the start, the green component starts to just kind of get held up a little bit by the material you're passing it through. It kind of sticks to it. As it continues, it continues to kind of start to lag behind. So your red component comes out and starts to separate and pull ahead of the green. And then hopefully at the end, what you've been able to do is completely separate the reds from the greens when it finishes flowing through this material at the other side. So in order for chromatography to work, you need what we call two different phases. The first phase is a mobile phase, and that's basically, you can think of it as the solvent for your mixture. This is what is going to basically make your mixture flow over that medium. So in gas chromatography, instead of a solvent per se, what we use is a gas, which we'll get to in a second. The second phase is that stationary phase. This is that medium that is making the compounds separate from each other. And typically this is some kind of adsorbent material. And I've said it a couple of times now, your compounds stick to the outside of this material. So it's called an adsorbent, not an absorbent. So this is just what your components are going to stick to so that they do separate. So moving on to gas chromatography in particular, the mobile phase that we're using is something that we call carrier gas, which in our gas chromatograph we use helium gas. Is that it's a nice inert gas that all it does is it kind of moves through the column, and the compounds, if there were no column, it would just, the mixture would flow through at an equal pace. But we do have a stationary phase. We have what's called a column. And this column is, if you think about it, it's basically a really long, thin tube that on the inside has some kind of adsorbent material that your compounds are going to stick to. And so once your compounds get loaded onto the column through the helium gas flow, they all start sticking to the material inside that column. In gas chromatography, the way we get the compounds to become unstuck from the column, to free themselves, is by heating the column to release them. And so just like distillation, The more volatile compound, the one with a lower boiling point, is the one that tends to come free more quickly. So the red ones kind of come off of the column first. And so they move along a little bit faster. They will come off, they'll stick again, they'll come off, they'll stick again. And yes, that is happening to the green ones. They are still flowing through the column, but they're not doing it as quickly as the red. And so you do end up having a separation of the components of the mixture that you put through. So the big takeaway here for this experiment is that your lower boiling point compounds will come out first. And then what I'm showing you is a picture of an actual chromatography column so that you can get an idea of it. So if you look, that is actually a very, very thin column that we pass these materials through. In fact, the first number there says 30M. That is the length of the column. This is a 30-meter long column. So what we have to do is wind it around and around and around into a coil so that we can actually fit it into our instrument. But the inside of that column is 0.32 millimeters in diameter, so not even a full half millimeter even. It's a very, very thin column, but it is very, very long, and you need that length in order to have the compound separate out very well. So here's just kind of a little diagram of what the instrument looks like. So you have basically a big box, which is the instrument itself, and the sample gets injected at the very top, at which point the material will move in, being directed by the flow of the helium. It gets brought in, and it goes down and goes around all of the loops of that column. And eventually, hopefully after they've been separated, it comes out over here, and those compounds will hit the detector. So you have your column, and remember, in order to get the compounds to free themselves from the column, we heat it up. And then the compounds eventually make their way through. They hit that detector, which basically it records when something hits it. And it sends that data out to a computer. So what do we actually see on that computer screen? Well, the detector is telling the computer every time it records that something has hit it and what time it hit it. And so you end up with a plot that shows the time, which we call the retention time, and the y-axis is the detector response, which you can basically think of as the number of hits at that particular time, the number of compounds that hit the detector. And so for the very first part, the clock basically starts the second that you inject the sample into the instrument. So that's time equals 0. And it does take some time for the materials to pass through the compound. So for a long time, you don't see anything on your plot. It's completely at baseline. There's nothing coming out and hitting the detector. Then all of a sudden, you do get a hit. And so this is your first compound that comes out. And so you'll see, hopefully, a very sharp, tall peak for your first compound. But hopefully, if all goes according to plan, you have actually separated your two different components. So you're going to have another portion where the detector isn't getting hit by anything, so it goes back to its baseline for a while. And then the second compound comes off, and so you'll see a second peak. And if you have 3 components, you'll see a third peak, and on and on and on. And then, of course, it'll go back to baseline. So just remember, the one that is closest to the origin is going to be the first compound that came off. And the second one will be farther away from the origin. So just knowing the boiling points of your compounds, you can make a prediction as to which peak is which. And now the only question that remains is, well, how much of each component did my mixture have? Well, it turns out that we can calculate that too, and luckily the computer actually does it for you. That's because the y-axis is the, sorry, my daughter's over here trying to distract me. So because that y-axis is basically the number of hits at that period of time, what we can do is integrate the areas of each of those curves to determine the ratio of each one. So let's just redraw that plot again and just show you what I'm talking about here. If I were to sum together the area of both signals and call that 100% of the signal, well, then I can figure out what percentage of that 100% corresponded to the green, and let's say it was 34%. Then the red part would be 66% of that total 100% area, which tells me that my mixture was 66% A and 34% B. How are you guys going to see this? You are going to be receiving a plot that shows you that trace that I just kind of hand drew, and then underneath there's going to be some data. So let's focus on the plot first that's on the top half of that screen. If you look at the x-axis as units, that unit is minutes, and so that tells you that this x-axis is that retention time. And so the first peak hit the detector first, and so that means that it is the lower boiling point component. You should be able to figure out which is your lower boiling component from what you have in your lab information. So the other thing that I did want to point out to you is it does give you an exact time for when that really peaked out, your detector response. The maximum detector response is listed up at the top of the peak for you. And that will also correspond to the retention time that is down in the data chart beneath. So if I zoom in on that data chart, what you see here is basically a plot of the data for each one of those peaks. And so if we look at the peak that has a retention time of 1.897 minutes, over on the left-hand side, it tells you that the percent area is 44.68 something something. And so what this is telling me is it's roughly 45% A, and then I can do the same thing with the second peak, and that'll tell me that it's about 55% B. Hopefully what you guys are going to see, this was the starting material that we used back in 2013, so it was roughly a 50-50 mixture of cyclohexane and toluene. Hopefully what your charts look like is you have one peak that's really, really big compared to the other. So you're going to have not 45-55, but hopefully, 80% something, or 90 or 95% something. And that is what you're going to be reporting. So you need to know the retention time so that you can tell which is cyclohexane and which signal is toluene, and then you're just going to report those percent areas. So I hope this makes sense. The other thing that I do want to do really quickly is just give you a really quick just verbal introduction to thin layer chromatography. So just like we said, gas chromatography has to have a mobile phase and a stationary phase. Thin layer chromatography also has both. So for thin layer chromatography, which we abbreviate as TLC, your stationary phase, hold on one second. Okay, your stationary phase is going to be a very thin layer of silica gel, and sometimes you use silica, sometimes you use alumina. In our case, we are using silica gel plates, and so what this basically looks like is it's a really, really thin plastic plate, that it has a very, very thin coating of silica sitting on top of it. Woo! Yay! So that's your mobile phase, or your stationary phase. Your mobile phase is just going to be a mixture of solvents. And so basically what happens is if we take this drawing and we rotate it around, this is actually going to be sitting inside kind of a pool of solvent. And you are going to have your components, your compounds, oops, spotted down at the bottom. You'll have one here, and then you might have another one sitting mixed in with it too. What's going to happen is this is actually sitting inside a container that has, let me draw the container really quickly, it's just going to be a beaker, and you're going to have some kind of solvent in it down at the bottom. Whoa, that doesn't work. We'll go for this blue, why not? It's going to be sitting in solvent, okay? Now that solvent is going to do what any liquid does when it sees a thin film of something. It's going to rise up the film. So this is going to, your solvent is going to go upward just like it would on a piece of paper. If you dip it into a liquid, that liquid tends to seep up the piece of paper. Well, what that is hopefully going to do for you is make it so that as your liquid rises up, you end up with a separation of your red versus your green. So that is the introduction that I'm going to give you to thin layer chromatography. You guys go through the theory of it in great, great detail in lab this week, and you just really don't need a big, huge introduction on it. So hopefully this video is going to help clear up how you're going to analyze your gas chromatographs and give you a good intro to lab this week. So sorry that it's taken me so long. This is literally the third time that I have recorded this video. I'm really hoping that it works this time and gets posted. And I will have another video for you next week. Bye.